Hey folks, how are you doing? Happy Friday. Um, let's go ahead and get started. We're talking about block modes of operation today, and I want to explain what we mean by that. So let's suppose we have written our AES code, and we have encrypted a block of 16 bytes, and everything checks out, but our file is larger than 16 bytes long, and so we're ready to start on the next 16 bytes. So we have this long string of data. We took a 16 byte chunk and we went through all of the different rounds of encryption, and then we got 16 bytes of plain text, or of ciphertext, sorry. And so now we're ready to start on the next 16 bytes. So what happens? So we could encrypt the next 16 bytes from scratch, just start over, go back to use the same key and the same key schedule that you used for the first 16 bytes. And we encrypt each block of 16 bytes exactly the same way. We call this ECB mode. ECB stands for Electronic Codebook, which is an archaic term here. The idea coming back from the old like book style codes, like the Japanese code, where you would open up your book, you would look up this block and see what it converted to, and then if you had the, then when you get to the next block, you open up the same book, you open up look up the block and that sort of thing. That the contents of the book don't change from block to block, and so that every time we encode a new 16 bytes, we do exactly the same thing we did before. And that works fine for text. For many years, we didn't see any problems with doing this, because text from English or text from any other language just doesn't have patterns that repeat every 16 bytes. But if we do use a file on we do use this mode on a file that's got data that repeats every 16 bytes, then we have a problem. And I want to show you exactly what that problem is here. I've got a short example here, and then I'm going to switch over and do a longer example in a moment. This is a picture of Tux the penguin, and when we encoded it in ECB mode, every white pixel in the shape got encoded in exactly the same way. They didn't stay white; they changed to other data. The encoding caused the pixel color to change, but all the white pixels encoded the same way. All the black pixels encoded the same way. All the yellow pixels encoded the same way. There's a little bit of subtlety right around the edges of the feet where we start getting like darker shades of yellow. But anybody who looked at the encrypted data here could still kind of make out the overall outline of the shape. And if this, instead of being a picture of a cartoon penguin, was a map with sensitive military locations or something like that, that encrypting graphic data where there are like solid patches that are all of the same color might not provide much security. That is, I can still get a lot of information even from looking at the encrypted version of this, because I'm encrypting lots and lots of blocks that are exactly identical, and so I'm getting out lots and lots of ciphered blocks that are identical as well. So here's the example that I wanted to sort of walk with you live through this. Give me a second to, here we go, switch over here. So I have a different cartoon picture here that's already loaded into my graphics processor here. And this is Bugs Bunny, and I'm going to encrypt this data using a program called OpenSSL. And what I'm going to do first is just bring my cursor down a few rows so that I'm not trying to type underneath my own picture here. So if we do OpenSSL, AES 128-bit mode ECB, and in we're going to take the Bugs Bunny data, and then out we'll call it Bugs Bunny ECB. Well, to show you what's happening here. Says it can't open this for reading because it's not got the wrong ending here. Let me try this again. Data and not raw. There we go. Enter the password here. So let's see. There's a password. I'm messing it up, so I'm having to type it over again. All right. So we've just encrypted it using ECB mode. It warns me, by the way, now that I'm using a deprecated mode here and gives me some suggestions that might be better. But that's okay. We're intentionally showing what's going to happen with this graphic image. This is the unencrypted version of Bugs Bunny. And so now if I open the version that's in ECB mode, here we go. Go ahead and open that up. It's 1920 by 3272. That's good. And that's what we get. We have now this encrypted version of Bugs Bunny, where the whites have changed to sort of a lighter gray. The gray is still gray. The carrot is gray. I mean, everything is, gray because, again, we're trying to create something that is similar to randomness, and so we're getting a lot of, shades that are sort of in the sort of the neutral color of the, neutral parts of the spectrum. But it's still entirely recognizable what character this was. That the encryption, because we're encrypting lots and lots of patches that have the same data over and over and over again, we're getting patches in a ciphertext that have the same data over and over again. And so that was recognized in the 70s as being a problem with the encryption schemes. Historically, we were encrypting messages, and messages were text, but if we wanted to encrypt other kinds of data, we might have some problems again. So let me talk about the approach to coming up with other modes that are more suitable for encoding, audio files and image files and things like that. So let me switch back here. There we go. So this is a different mode. It's called CBC Mode. This stands for Cipher Blockchain. And it uses a slightly different encryption process for every block after the first. We're going to go ahead and encode the first block normally. And then when we get to the second block, and from every block from that point on, we change the very first add round key in the block from just XORing the plain text with the first key from the key scheduler. We're going to XOR the plain text with the first key from the key scheduler and the ciphertext from the previous round, and then all of the other round key steps stay the same. So what's happening now is that we have this long block of text. We're going to take the first 16 bytes, and we're going to send it through all the different steps in the encryption. So round 1 involves an add round key, then an S box, then shift rows, then mix columns, and then we go back and we do this round a whole bunch of times. The last round replaces the mix columns with another add round key instead. And finally, we get to our ciphertext. And we get the first 16 bytes of our ciphertext. So when we then start with the next 16 bytes, to prevent the output from being the same, if these two blocks are the same, if sort of this is a bunch of white pixels and this is also a bunch of white pixels, we're going to, that very first add round key, before we do any of the other encryption steps, we're going to incorporate the ciphertext from the previous round into that add round key step. So we're going to take that ciphertext plus the plain text plus the first key, and that's going to be the first step in the new process, and then we go through the rest of the process as before. All the other add round keys in this in here stay the same. It's only the very first round where we are incorporating the ciphertext. Okay. There are some implementations of CBC that also use what's called an initialization vector, so that even the very first round is has something to XOR with in the first round. For our purposes, we're just going to use an initialization vector that's all zeros, which is the same as like not XORing with anything. We're not going to worry about the initialization vector. But CBC just changes what we do if we have to do multiple rounds of encryption. We chain the ciphertext into the beginning step of the next round, so that the output from each round will be different even if the inputs are all the same. Okay? So there are other ways of addressing the weakness of ECB mode. If you read through the NIST specs for AES, they describe some of the other modes. One of them is, for example, to use an LFSR to generate a stream of bits instead of using the ciphertext to XOR. And there are other ways of doing that, but the point is that there is a weakness in using ECB mode to encrypt data that's not just raw text, and so you want to have built into your AES implementation some way of overcoming that weakness, and CBC is perfectly adequate, and it is also by far the most commonly used encryption mode for data. There are other modes that are used in specialized contexts, and we just don't really have the time to go over all the different ones because they're just variations on the same thing. Okay, but this is like the final little bit of your project is once you've got encryption working for one block, set a flag to test whether you're encrypting in ECB mode or CBC mode. And depending on whether that flag is active, change the very first XOR step in your encryption. And then you have a more robust encryption mode called CBC mode. Okay? All right. Have a great weekend. Y'all take care.